This video series is intended to introduce new users to the distributed energy modeling tool DIRCam, developed by Lawrence Berkeley National Lab. In this and the following videos, we'll help walk you through the basic concepts of DIRCam, how the tool works, how to create and customize system models, navigate and interpret results, make use of advanced modeling features and options, and debug issues that might arise as you use the tool. First though, let's introduce you to the tool. DIRCam, which stands for the Distributed Energy Resources Customer Adoption Model, is a decision support tool that leverages powerful optimization algorithms to guide the planning, design, and analysis of decentralized energy systems and microgrids. Beyond this video series, you can learn more about DIRCam, including how to access the tool, at dircam.lbl.gov. If you're watching this video, it's perhaps safe to assume you're somewhat familiar with distributed energy resources and microgrids, and the technical and economic benefits they might offer. Still, to help illustrate how DIRCam works, let's start with the basics. The motivations to deploy DERs or microgrid vary a lot by application. They might focus on reducing energy costs by replacing imported energy with energy generated locally, reducing environmental impacts like CO2 emissions by installing renewable resources like solar PV, or adding operational resiliency by deploying full microgrid capabilities which allow the site to operate as an island when grid power is disrupted. This new energy system could also be designed to capture some combination of all of these benefits. It's important to note that for each of these objectives, the optimal system design will vary significantly based on a number of site-specific characteristics. This isn't unusual. Microgrid designs are often highly customized to their particular application. Important characteristics to consider when designing a microgrid solution include energy rates and tariff structures, energy consumption patterns and load profiles across different end uses like heating, cooling, and direct electricity consumption, local climate and site data that might influence the suitability of different DER technologies, information about the DER technologies themselves, which are being considered for deployment, their technical performance characteristics, and capital and O&M costs. And finally, for larger sites, such as multi-building campuses, where the placement of distributed resources might impact performance, the topology or structure of the electrical and thermal networks that connect the buildings. Deploying distributed energy systems and microgrids is often a long and complex process, but the first step is to develop a feasible, actionable design. Specific information to assess the feasibility of a given design include basic cost and performance metrics like total capital costs, net changes to annual operation costs, and the payback period for new investments, the portfolio of which new technologies that should be installed, and the capacities of each, information on how those technologies are dispatched under typical conditions, and for larger sites, where within their internal networks each DER will be placed. Given all of these factors, it's clear that the process of designing a microgrid system is by no means simple. Fortunately, this is precisely the problem DIRCam has been developed to address. DIRCam is powered by state-of-the-art optimization algorithms developed at Berkeley Lab to find the optimal DER design solution by simultaneously considering a range of value streams for each DER asset, including reducing energy imports, load shifting and demand charge management, revenue from electricity sales, as well as providing demand response and ancillary services back to the grid. DIRCam solves this problem holistically, assessing the potential of each technology to compete with or complement one another across each value stream, and selects a design that maximizes total system value based on the user's defined objectives and constraints. One key thing to note: there are, of course, other software tools that assist with microgrid design. Several of these tools use a simulation approach to find a solution, rather than the optimization approach used by DIRCam. I want to take a moment to highlight key differences between these approaches. Simulation can be very useful, as it often allows for a more detailed examination of operation conditions, for instance by modeling all 8,760 hours in a year. For dispatch of DER technologies, however, simulation typically relies on rules-based strategies. When certain conditions are met, different DERs might be dispatched to respond in a scripted manner. Rules-based control strategies can vary in complexity, but in practice, they are often influenced by the past experience or preconceptions of the modeler. As a result, the simulation approach does not guarantee an optimal solution. Optimization, on the other hand, as used by DIRCam, does not rely on user-defined rules for dispatching. Rather, the DIRCam model defines constraints for how technologies can and cannot operate, and then lets the optimization determine how they are dispatched at each point in time by adhering to these operational constraints. This means the optimization approach is able to search across a wider solution space to find an optimal design. However, to keep the optimization problem size manageable, DIRCam must incorporate some simplifications that can reduce the level of detail compared to simulations. There are two major simplifications in DIRCam that should be highlighted here, the first being design days. Rather than modeling each day of the year, DIRCam uses a smaller set of design days to capture seasonal and operational variation. By default, DIRCam uses 36 design days, one for each month across 3 day types: typical weekday, typical weekend day, and peak day. This peak day type is intended to represent the 3 days each month where loads are highest. It's typically these days that will set electricity demand charges, which can comprise a significant fraction of monthly electricity costs, and can thus have a lot of influence over optimal system design. Users can add additional design day types to capture events like outages, demand response events, or critical peak pricing events, but in general, the variety of days is reduced significantly compared to a full 365-day design period. The second key simplification is linearization. DIRCam is a mixed integer linear model, meaning all constraints must be captured in a linear fashion. Some DER technologies exhibit nonlinear behaviors in the real world, and so these must be simplified to be included in DIRCam. Because of their relative strengths and weaknesses, many microgrid design workflows will in fact incorporate both an open-ended optimization approach to explore and understand early-stage feasibility, and more detail-oriented simulation exercises later in the process to vet and refine system designs. In this regard, DIRCam can be seen as complementary to other simulation-based software tools in this space. Now that you're familiar with the basics of how the model works, let's get to the question of what you can do with DIRCam. DIRCam provides data libraries for typical building loads, solar insolation, electricity tariffs, and DER technologies to help you quickly construct new models, while offering you the option to customize any of these data fields. With DIRCam, you can build simple models for quick feasibility studies of single sites. You can also develop more complex, multi-run scenario analysis to explore the impacts of key site characteristics on design outcomes like DER technologies and costs, energy rates and tariff structures, load consumption characteristics, as well as energy policy impacts and innumerable other model parameters. This is particularly useful when you need to develop a single design solution capable of delivering strong economic or technical performance despite some uncertainty in the eventual real-world operating conditions of the microgrid. Finally, you can construct more complex microgrid representations that include optimizing power and heat flows within multi-node microgrid models and find resilient, security-constrained designs for larger-scale, critical facility and off-grid applications. Given the ease of setting up an initial DIRCam model, analysis often involves an iterative process in which site inputs are defined, design objectives selected, and optimized results explored. The insights from an initial round of analysis can then be refined to help you further explore key design questions and uncertainties, allowing you to proceed to the next steps of your project with confidence in your design solution. The software that powers DIRCam consists of 3 components: the underlying optimization engine, which is often simply referred to as DIRCam, the server which connects users to the optimization engine, and the user interface that provides a structured environment for users to build, modify, and explore their microgrid models. This interface is often referred to as DIRCam Desktop or the DIRCam UI. DIRCam uses a proprietary optimization language called GAMS and a powerful proprietary solver, CPLEX, to quickly solve even highly complex system models. Consequently, Berkeley Lab has adopted this server-based architecture to allow users to connect with DIRCam without the need to purchase and install additional third-party software. Currently, the latest software versions are version 5.9 of the DIRCam optimization engine, which connects with version 2.5 of the DIRCam desktop interface. Incremental updates to both these components may be released after this video series, but information provided here and in subsequent videos should remain broadly relevant. DIRCam is free to use. You can register for access to the desktop interface at dircam.lbl.gov. Berkeley Lab also offers an alternative browser-based interface. For free access to this version, please contact us at durcam@lbl.gov. In the next video in this series, we'll discuss the general workflow for creating a model in DurCam. From there, we'll dive into detailed examples to help you understand the variety of design problems where DurCam can add value. If you have any questions that aren't addressed in our tutorial videos, we encourage you to reach out to us directly. You can always email us at durcam@lbl.gov.